Welcome to the third part of our workshop, Python for Geospatial Big Data and Data Science using the FASRC. In this third chapter, we are looking into how to transfer what we programmed on our local machines now to the FASRC to actually use it, to run our programs there, and what to keep in mind and how it's different in terms of environment and what we have to think about. There is a lot of differences between a local environment and a high-performance cluster environment. These are just some bullet points here, and I won't discuss all of them. As I said, the slides have more comments on each of these points, so if you're interested, have a look at the slides and their comments. Basically, what we can discuss here is, of course, the environment is different, the dependencies are different. Probably we can't install everything that we can install on our local machines on a shared system that's not only used by us, but by many, many people at the same time. Then there is a batch system, that's our Slurm scheduler that we discussed earlier, that we don't have on a local machine, because on a local machine we are usually the only user and we just run and execute a program whenever we feel like we should. So here we have to ask, please scheduler, make sure we have these and that resources and find the best time and place on in terms of which node to execute it, where all these requirements can be met. That's not necessarily always in an instance, instantaneously, that can take a while until we get there. Then there's data transfers, as we discussed in the first chapter. It's very important to consider how to get data into the cluster, what to do about the data, where is it stored, and which site is it stored. Here in this case, we have different sites like the Boston site and the Holyoke site, how to handle that. And all these things need to be considered that we never have to deal with on our local machines. And lastly, error handling and debugging is something that is dramatically different, because if we submit a job to our Slurm scheduler, we don't get feedback from what our program says, at least not in the same way. Of course, there are ways that we will discuss here, but it's just not as easy as waiting for some print statements that we send to standard out on our terminal to obtain if something worked or not. And there are a few other things that we should discuss. Optimization is mostly the topic of the fourth chapter, so that's more the most computer sciencey chapter, how to really make sure that we can leverage the performance of such a cluster. But we will get there. Now, first, let's copy our script to the FASRC. Here in the slides, I suggest using SCP, which is the SSH version of the copy command. -R means recursively everything that is in our current directory, so watch out where you execute that, probably ideally not in your home folder locally, because that's probably crowded. And then to the address there. Of course, replace user with your own FASRC username, then the login node, and then :/destination. Destination is then the path to wherever you want to store this. That can be on the global scratch, or that can be in your home folder, or just in a specific folder you want to create for this project, or that you should have created the folder already. So make sure the folder is existing before you run this. Alternatively, you can do this through the web interface. I found that pretty convenient, just to start a small Jupyter instance there, and then you will end up in your home folder, and there you can easily edit all the files that you see with this web interface. So, for example, if you run something, then make a small change, you don't have to use SCP all the time. That is a little bit cumbersome sometimes, because you always have to re-authenticate yourself with your Harvard key and especially not the Harvard key, with the FASRC password and the two-factor authentication code that you need. So sometimes it's a bit more easy to do this over a web interface, but if you copy the entire project that contains maybe multiple files, it makes perfect sense to do it that way. Next step then would be to test that in an interactive session. We discussed that as well in the first chapter of this course, where we said you can, with Slurm, basically have two modes of operation. One is to submit a task asynchronously, and the second is to have an interactive session that just feels like an SSH session to a remote location, where you then get a terminal, a command line interface in which you can walk around and move around and run programs as you're used to. And that makes a lot of sense to see if something is running. So coming from your toy example that you developed locally on your machine, and then copying this onto the cluster, it makes a lot of sense to not change it in the first place, but just see if it runs and if it works as you expect in an interactive session here. Feedback and output, how to obtain results, because ultimately our script here is written to generate some output, some analysis results here that we can then use for our scientific paper or whatever we intend to. Most programs that we run, we want some outcome out of them. That probably makes sense. And that's also just a little bit different if we compare it from our local machine to our cluster here. Because, as I said, especially when running something asynchronously, you don't get all the outputs into your terminal. And therefore, Slurm offers you an option to write all the standard out and all the error messages into separate files. And then you can specify, hey, here is a file, please use that for each time you run the script, and put everything that I usually just put in a print statement, or I have some more advanced logging system in place that logs this to standard out. Like standard out is what you usually see on a terminal. If you run something and then print something and then it gets printed, that is called standard out. That is then written into this file that you can specify there, as well as error messages. That's something to keep in mind, and therefore just to check that and to get a feeling if that works and how that works, it makes sense for your test script here just to have some regular print statements for every chapter, for example. You can, for example, sometimes use a little argument if you want to equip your script with to handle arguments. You can, for example, look at the package argparse, and then you can create an argument to say, like, I deactivate and activate the print statements as I desire, because sometimes it's just nicer to have a program that runs cleanly. But especially for testing purposes, it really makes sense to give yourself a way to follow a little bit what's happening when it runs remotely. So I suggest to create print statements for all important parts of your code. So you loaded something, you loaded a second thing, you merged something that worked, because that also gives you an idea of where something failed. Because if you have the first 3 print statements but not the fourth, then you know that between the third and the fourth something broke. There are more elaborate ways in software development, definitely, than print statements, absolutely. But for the purpose of this here, let's focus on print statements for now. And then also make sure that you write your results to a separate file, because we discussed that the scratch on the node might not be suitable for such purposes. So just make sure that your result, that you, for example, the difference in precipitation dependent sentiment change, complicated way to say it, like the difference in sentiment depend on rainy days or not rainy days, as aggregated as however you did it, for example, per country, that this is written to a file in, for example, your home folder. That's a perfect example of how to use the home folder storage to have this. Once every time you run it, there is an update to this file. That's perfectly fine. It's just the home folder isn't used or isn't suitable for heavy I/O, where you really often read something, write something, read something, write something. That's better done on a scratch side. But for example, for results, to save results and to write them off, the home folder is really suited for that. Slurm's S-batch jobs. Now, a few times now mentioned the interactive session. So far, you have probably done that already, and you saw commands. And I also said there is a way to interact with the cluster in an asynchronous manner. That means you submit a job, you tell them, please execute this and that command here, and then do that asynchronously, so I don't need my connection open, for example, via the VPN, via the Wi-Fi, and I want to use I want to shut down my computer, for example, and this just runs in the background. This is something what you can do with S-batch jobs. That basically just executes a script that you write, like a shell script, and you point Slurm towards that script, and within that script you define all the resources that you want and what to do once Slurm starts the script on a compute node. This here is an example of such an S-batch job. Here we define how many cores do we want, for how long this job should run, and on which partition, how much memory we want, and where to write our standard out and our errors to. So here we create some files. I before I started that, I created a folder called results, just to keep everything a bit tidy. Then I have this file job underscore std out underscore %j. J is then filled with the job ID, so I have separate files for every time I run this, because every time I run this I get assigned another job ID. The same for errors, and then I have some files where I can later read if something went wrong, or to check if everything went well. So I have that. There are a few more commands that you can use or might use. You can just Google Slurm, because that's a tool that's not only used here for the FASRC, but in multiple sites and contexts, and just exists independently. But you also have, I think, here the documentation of the FASRC team to read about it. For example, one command that I didn't list here, but that might be very handy, is you can ask it to send you an email once your job is done. That's a very convenient way, because especially when the job is done, not only in 2 or 3 minutes, like in our examples here, but maybe 10, but for example, it runs for hours or even days, then you definitely want to in some kind of information when it makes sense to really have a second look, because you expect your data to be done. After specifying all these Slurm-specific information, you then go on with the commands that should be executed on the compute node, exactly as you would do in your own shell when you do this in your own interactive session or in your command line. So for example, here I first load all the environment in specific modules like Python, Mamba, and everything that belongs there that I can actually work with it. Then after I have Mamba available, that's by the way something you can try. Without loading without loading the Mamba module, you can't run Python, you can't run Conda, you can't run Mamba. Once you run that's a job for a few milliseconds. That goes really quickly. Then all these commands are made available. So that's a really cool tool here. So first load that, then load your environment, your Python environment, with all the dependencies of your script. For example, pandas is what you have used, or xarray is what we use to work with these netcdf files. What else might be there? Maybe matplotlib if you have a plot or something. All these tools that are used for your script. And then actually just run the script that you wrote. So here in my case, I called it precipitation sentiment toy example chapter 3, because that's the file that you find in the chapter 3 folder of the repository of this course. This is an example, a working example of a Slurm ASBatch job. And once you put that into your folder, you can then just call Slurm and ask it to run this remotely on a compute node. Now, when it does that, then you're just left with, thank you very much, I accept your job, and you don't have any more information. But now I guess you want to monitor that, because you're eagerly awaiting some results and want to find out, did that work, or is it still running? Is it everything as I expected? There are different things that you can do. For example, you can connect to the compute node that your script runs on if you find out find the ID about that. There is a link in the cheat sheet where you get to a web interface of the FASRC that shows you all the jobs that are currently running and the node IDs. And with this node ID, you can then connect in a second session to this node, for example. And then you can run htop or just top or ps-uppercase U and then your username. That gives you a list of all the processes that are running in your name. That is very handy to see how many processes are there running, especially if you're included multi or parallelization in your program. Then you can see if there are really different processes being started in your script here. Or with using htop, you will see all the processes that are running on this node. So all of the processes, for sure, several hundreds of them simultaneously, really. But you will be able to monitor that and see, like, okay, here are my 5 processes, and they really cause 100% of load, because that's what you want to achieve. If you do that at that stage of the workshop, you will have only one process that does something, but at least that should really work full throttle. You can also, from any node in the network, list all the running Slurm jobs, and you can use sq, written together, sq. The sq command that gives you a list of all the processes there, or as I said, there's this website that you can also use to monitor that. The link is in the cheat sheet. Now, exercise 1. transfer your script to the FASRC using your preferred way, either SCP we discussed, or we also discussed going through the Jupyter Notebook environment where you can just create a new file and copy the contents into that. And then, of course, adjust the paths to your dataset, because if you've worked so far locally on your machine, then you probably downloaded the data from most likely from our Google Drive there, or you went through the sources of the data sets and downloaded a full copy of that to your local device, which is perfect. But now, on the cluster, obviously, the cluster does not have access to your local data set, of course. We copied the entire data set to the cluster so you can use it, and you will have the link in the cheat sheet document that I always mention. This cheat sheet is also part of the repository, and there you find, I think in the bottom of the second page, you find a path where it is located on the cluster with global read access. So you can just insert this and should be able to replace that with the path to the data set that you used locally. If that doesn't work right away, then it makes sense to make sure that the folders are exactly named as we did in our examples, but then it should just work. What you can also do, to try that in the first place, is run that in an interactive session, because this will just be much easier to give you some feedback. And chances are that there will be some data missing, data is not found because there is some hiccups with the references to the data set, all these sorts of things. So that's just a bit easier in an interactive session to deal with. What I also suggest is that you time how long it takes to execute something. In the exercise sheet, I have a little example of how to do that. The basic idea is you just get a timestamp before you run something that probably takes a while to execute, or for the entire script. Take a timestamp, and then after you're done, take a second timestamp, and then subtract one from another. And this difference is obviously the time that has passed between you took these two measurements. And therefore, you know how long it took to execute that. Now, with this time that we have through this in mind, we can then continue to optimize our performance a little bit, because we want to really find out where's the bottleneck, where's something not working as expected. Because, hey, the FASRC comes with hundreds of high-performance nodes. Right? We saw the stats, right? 48 cores, 200 gigabytes of memory, incredibly fast bandwidth in the network. That should just excel everything we have seen so far when working in on this project. And to really make sure how fast it is and how much faster it is, take the time and measure it and get an understanding of how long does it take on the cluster and how long does it take on your local machine. Then, the second step, also run the same thing as an as-batch job using our template here, and make sure you get it to run asynchronously without being in an interactive session in which you have to be logged into the thing, and also try to monitor that. So while it is running, try to connect to the exact same compute node. That's one thing that you can do, or maybe just start with checking what are the processes running in my name using Slurm. That was the SQ command, and check what's running there. Is it really working as I expected? You'll find the entire exercise sheet here, scanning this QR code that points you to the GitHub repository, and the file should look like this. And I wish you all the best with that and a lot of fun. Here in chapter 3, we learned how to transfer scripts from a local environment to a remote environment on the cluster, and the required changes that our code needs. That is paths to files, obviously, logs, because we probably don't have standard out. We might have standard out on the interactive session, but not for the asynchronous as-batch job. And that we have to write our results to a specific path in ideally our home folder. In this case, that will do. And then also we were discussing running scripts interactively or asynchronously using an interactive Slurm session or an as-batch script. Thank you very much for your attention. Enjoy the exercise, and I hope to see you in our last chapter 4.